Hi guys, I'm Monica. Welcome to my channel Aeroker. So in this video, we're going to take up a very small topic, yet an important one, that is the pressure coefficient. Now, what is pressure coefficient? Pressure coefficient is the dimensionless pressure that we measure, and this we can denote it with Cp. So it can be denoted by Cp, which can be written as P minus P infinity by Q infinity. What is this Q infinity? Q infinity is half rho infinity V infinity square. Now this equation 1, that is our Cp, it is valid throughout aerodynamics, right from the incompressible flow to the hypersonic flow. So if I want to write Cp for an incompressible flow, it can be expressed in terms of velocity only. So how can we do that? Let us have a look. For example, I have some arbitrary aerodynamic body. This is our aerodynamic body, which is immersed in a flow, free stream flow. This is immersed in a free stream flow where the pressure is P infinity and the velocity is V infinity. All right. So let us choose any arbitrary point in the flow. Maybe let us consider this point over here. Okay. Here, arbitrary point in the flow where the pressure are P and V. So let us say at this point, at this arbitrary point, I have pressure P and V respectively. So using the Bernoulli's equation on this flow, I can write as P infinity plus half rho V infinity square is equal to P plus half rho V square. Or I can also write it as P minus P infinity equal to half rho into V infinity square minus V square. Let us say this is our equation 2. Now, what if I substitute this equation 2 in equation 1? What happens to Cp? Let us have a look. So here we have half rho V infinity square minus V square by dynamic pressure would be half rho V infinity square. Correct? Now here I am telling that my flow is incompressible. So for incompressible flow, what happens to the above equation? What happens to Cp? So when I solve it mathematically, I get this term as 1 minus V by V infinity whole square. Let us say this is our equation 3. Now this equation, as we said that the flow is incompressible, it holds for incompressible flow only. So this is to be kept in mind. So we have some important conclusions, some important points coming out from this equation 3. What are those? Let us have a look. Now from equation 3, you can see that the pressure coefficient at a stagnation point, that is where V is equal to 0 in an incompressible flow, would be always equal to 1. Correct? So this is for stagnation point. So this value of 1, Cp is equal to 1, this is the highest allowable value. So you cannot get Cp beyond this. So this is the highest allowable value that you can get for Cp anywhere in the flow field. This was about incompressible flows. Now what if I say that my flows are compressible? So if my flows are compressible and at stagnation point and compressible flow, my Cp can be greater than 1, which is not possible in the incompressible flows. Now in the regions, there is one more conclusion coming out. In the regions where V is greater than V infinity, that is, we have considered one point and the other would be the free stream properties, right? So in case my V is greater than V infinity, or maybe my P is less than P infinity, Cp will be negative. Cp will get a negative value. One more interesting property we can see with respect to Cp. What if I rearrange equation 1, this equation, if we just rearrange in such a way that I get P is equal to P infinity plus Q infinity into Cp. So by looking at this equation, the value of Cp would clearly tell me that how much P differs from P infinity. That is how much the free stream pressure and the pressure at that point differs with the in multiples of dynamic pressure. How? Let us have a look in more detailed view. So for example, if I say Cp is equal to 1, then how would the equation turn out? It would be P infinity plus Q infinity, or the local pressure is 1 times the dynamic pressure above the free stream static pressure, correct? So if I have Cp is equal to -3, then what will happen to this equation, which would be P is equal to P infinity minus 3 into Q infinity, which means the local pressure is 3 times the dynamic pressure below the free stream static pressure. So these are the conclusions that we can get if we rearrange the equation for Cp. Now moving on to our next topic, that is what conditions we have on velocity for incompressible flow. So let us see what are the conditions on velocity for incompressible flow. So the moment I say incompressible flow, what comes to our mind? Rho can be assumed to be constant. Now what is rho? Rho is mass per unit volume, and here we are saying that rho is constant, which means a fluid element of fixed mass moving through an incompressible flow must also have a fixed constant volume, correct? So now we know one more term, that this term is nothing but physically the time rate of change of volume of a moving fluid element per unit volume, correct? This mathematical term denotes that physically the time rate of change of the volume of a moving fluid element per unit volume. Now, just now we have stated that for an incompressible flow, the volume of a fluid element is constant. So which means for an incompressible flow, can I write this term as 0? Correct? Let us say this is our equation 4. And keep in mind this is for incompressible flow. So this, we came to this conclusion with the help of the definitions. So for an incompressible flow, what I can say, what is this term called as? The divergence of velocity. I can say that the divergence of velocity is 0. There is one more method that we can come to this conclusion. How? By using the continuity equation. So if I take the continuity equation, that is dou rho by dou t, and this term is equal to 0. So this is our continuity equation. So for incompressible flow, what happens to rho? Rho is equal to constant, and also dou rho by dou t becomes 0 in this case. That is for an incompressible flow. So can I write this term as this, because rho is constant over here, right? So which means my dou rho by dou t is already 0. Then I have rho into divergence of V. So what is divergence? Rho is constant. Then I am remaining with the term this. So with the help of continuity equation as well, we can come to this conclusion. So this was the point of Cp, that is the pressure coefficient, and this term pressure coefficient is used in many aerodynamic calculations. The reason that we use this non-dimensional pressure term, it eases our calculations at most of the times. That is why we have learned about this term called pressure coefficient. And also the important point that we have to remember, that the divergence of velocity is equal to 0 when it comes to an incompressible flow. So this was it. We will discuss furthermore more interesting topics. Thank you for listening. Stay tuned.